Let's dive right into this explainer and see how we can take the radically different computing paradigm of quantum mechanics and use it to literally smash through the current barriers of computational mechanics. Today, we're looking at a totally fascinating paper by Ortiz and Cirak that argues the very foundations of how we compute solid mechanics might be on the edge of a massive exponential shift. To really get why we urgently need this shift, we kind of have to rewind and look at the history of our computational power. The phenomenal advances in computational mechanics from its early days in the late 1950s to right now, well, they perfectly mirror an exponential increase in computing power. Finite element problem sizes have absolutely exploded, going from less than 100 elements in those early days to hundreds of billions of elements today. That's more than 10 to the 11th power. And for decades, this scaling has basically just ridden the wave of Moore's law, doubling transistor density every 2 years. But, here's the real problem. What happens when Moore's law dies? We are literally hitting a computational brick wall. The general consensus now is that future improvements in classical computing power are going to be severely limited just by the sheer physics of shrinking logic gates any further. A naive scaling up of our current computing tech without that increase in transistor density is fundamentally impossible. It would just cost way too much and consume absurd amounts of energy. So we desperately need a way out of this impasse. So here is our roadmap for getting over that wall today. 1. The finite element ceiling. 2. The quantum paradigm shift. 3. Quantum basics for engineers. 4. Simulating microstructured materials. And 5. Exponential acceleration in RVEs. Okay, section 1. The finite element ceiling. Tracing this history, it becomes super clear that to keep scaling our models for really complex structures, we simply cannot rely on classical computing architectures anymore. We started out in the 1950s with highly simplified, tiny models. By the 1980s, brilliant minds were already dreaming up quantum computers, specifically because they saw this classical ceiling approaching. And now, in the 2020s, our finite element analysis models routinely exceed hundreds of billions of elements, directly colliding with the end of transistor scaling. Which brings us to section 2, the quantum paradigm shift. Now, the pioneers from the 80s we just mentioned, their ideas aren't just historical fun facts. They are the fundamental engineering proofs for why the quantum computing paradigm must exist. Take Richard Feynman, right? He realized that the state of a quantum system with just a handful of particles has degrees of freedom that scale to 10 to the power of 3 times the number of particles. If you try to discretize that space classically, it's completely unsolvable. There's just not enough memory in the universe. On the flip side, Paul Benioff approached it from an energy perspective. He pointed out that a classical AND gate has 2 inputs but only 1 output. It's irreversible. You can't work backwards from the output to deduce the inputs. This irreversibility destroys information, and restoring information fundamentally dissipates heat, which puts a hard cap on classical efficiency. So, the absolutely crucial point here is summed up perfectly by Feynman. To simulate nature accurately, especially at massive scales, we need machines that actually operate on the very same rules as nature. You just cannot efficiently simulate a quantum reality on a classical machine. You need a quantum machine. All right, let's get into section 3, quantum basics for engineers. Now, I know quantum mechanics can sound deeply intimidating, like it's some dark art reserved only for theoretical physicists. But I promise you, as engineers, you already speak the underlying language fluently. If we map these concepts out, you'll see that a quantum state vector in that fancy-sounding Dirac notation is quite literally just a complex vector. And a quantum gate, which sounds incredibly sci-fi, is really just a unitary matrix multiplying that vector. The math is exactly the same. It's just wearing a different hat. A state vector describing the configuration of a quantum system is mathematically playing in the exact same linear algebra sandbox you're already used to. You have the standard classical notation for a vector in a complex space, and then you have the exact same concept written as a ket with a vertical bar and an angle bracket. That is literally all Dirac notation is. And extending that idea, evolving a quantum state from an initial setup to a final output is just applying a matrix transformation. When you hear the term quantum operator, just think matrix. A universal quantum computer does its computations simply by taking a chosen initial state vector and evolving it to a final state vector using user-designed unitary matrix transformations. It is pure, unadulterated linear algebra. But here's where the linear algebra actually gets kind of magical. Because of superposition, a quantum system can evaluate all possible basis states simultaneously, granting us what is known as quantum parallelism. A single qubit isn't just rigidly a 0 or a 1. It's a linear combination of both, defined by complex coefficients called amplitudes. So instead of crunching one possibility at a time, we evolve the whole system in one fell swoop. And then we have entanglement. This is the wild phenomenon where a multi-qubit state cannot be separated out into the individual independent states of its qubits. This entanglement means the state space of a quantum system is exponentially larger than a classical system with the same number of particles. For n qubits, your state space is 2 to the power of n. This exponential explosion, that is the absolute secret sauce for massive data encoding. Moving on to Section 4, Simulating Microstructured Materials. Let's ground this in our model problem and see how this builds into something insanely practical for applied mechanics: computational homogenization. To figure out how complex materials like multi-phase composites or polycrystalline structures actually behave, we have to bridge 3 totally separate scales. You've got the macroscopic scale of the whole structure, you have the mesoscopic scale, which is an intermediate material point, usually represented by a representative volume element or RVE, and finally, you have the microscopic subgrid, resolving the actual granular microstructure. Capturing this microscopic subgrid accurately without cutting corners is absolutely essential for the fidelity of the overall simulation. If we want true, uncompromised fidelity, we need that granular resolution. But here is the massive bottleneck. Every single time your macroscopic finite element solver asks for a stress update at just one integration point, you have to run a full microscale RVE calculation. Doing this concurrently on the fly for a massive structure, that is the exact computational brick wall we talked about earlier. It is simply way too computationally costly for even the world's absolute largest supercomputers. Classically, we've been solving these cubic RVE problems using a fast Fourier transform, or FFT method. You basically apply an average strain to the RVE, transform the problem into Fourier space, and then solve for the local fluctuating displacement fields using a fixed point iteration to find your effective, homogenized material properties. It's a highly optimized algorithm, sure, but classical computers just cannot run it fast enough across millions of macroscopic integration points. And finally, Section 5, Exponential Acceleration in RVEs. Okay, here comes the absolute mic drop. Replacing the classical FFT solver with a quantum solver. The classical fast Fourier transform has a computational complexity of big O of n log n, where n is the number of degrees of freedom. That linear dependence on n severely limits the size of the RVE you can simulate. But by encoding the mechanical states as quantum amplitudes and using the quantum Fourier transform, or 2FT, the complexity drops drastically to big O of log n to the power of c. This is known as polylogarithmic complexity, and it is an unbelievable exponential leap in computational performance. And here's why that matters so profoundly. Because the computational cost drops so drastically, we no longer have to simplify or approximate the subgrid. We can compute with radically higher fidelity, capturing the true granular nature of microstructured materials without crashing the entire system. Listen, this isn't just some incremental, slightly faster processor type of upgrade. It is a fundamental paradigm shift. By rethinking how we encode polynomials and state vectors into quantum gates, the researchers have shown that an exponential acceleration is highly mathematically viable. This finally takes concurrent micro-macro simulations out of the realm of pure theory and drags them much closer to routine engineering practicality. Which leaves us with this final, kind of mind-blowing thought. If we can actually solve complex microstructures almost instantly and with incredible fidelity using quantum parallelism, completely escaping the classical finite element wall, what exotic metamaterials, aerospace composites, or next-generation structural mysteries could we engineer? What are you going to design first when you literally have the power of nature's own computer at your fingertips? Think about it. Thanks for checking out this explainer, and keep questioning the limits of what's possible.